Apparently, sometimes I don't watch the news.
We interrupt
because
our
I'm a
program
kid,
to bring
and
you
apparently
this
every time,
important message.
apparently Grandpa just gives me the remote after we watch the Powerball.
What I wanted to get to today is something that a lot of you have commented on, and that is the receptor for the SARS-CoV-2 virus that causes COVID-19, and that is the ACE2 receptor. The ACE2 receptor is how the virus gets into the cell. It's the doorway, and it's more than just a doorway, and today we're going to be talking about exactly what the ACE2 receptor is and what it's involved in and why that matters. I've been wanting to do this for a long time, but the more I looked into it, the more complicated and interesting at the same time that it was. So I wanted to do the research first and then tell you where we are right now. This has reached a head because there are a number of people out there that are actually taking different sides on this issue of the receptor. So what it boils down to basically is, as we've talked before, outside of the cell or on the surface of the cell, there is a receptor for the SARS-CoV-2 virus, which is the thing that causes COVID-19, which is the coronavirus. And so here we have the virus, and it's got these projections that make it look like rays of the sun. That's why it's called a coronavirus. This is SARS-CoV-2. This is 2019 coronavirus. Here is the S protein that we've talked about. And the receptor for this is on the surface of the cell, specifically cells that are found in the lung, the type 2 pneumocyte it's known as, and also in the GI tract. And this receptor is known as ACE2. And that's really important for you to understand, ACE2. This is where the S protein docks, and then there's another protein called a serine protease, which is also here in the membrane, which helps to internalize this virus into the cell, and it allows the messenger RNA, which is in here, to come in and infect the cell. The key here, though, is this protein that is on the side of the cell is ACE2, and it's exactly the same protein that was the receptor for the SARS-CoV virus that was back in 2002. So the question is, why is this such a problem? Well, there is some animal data that angiotensin receptor blockers, which is a very common type of high blood pressure medication, and ACE inhibitors, which is another common type of blood pressure medications, can increase the concentration of these ACE2 receptors on the surface of the cell. So how do you know if you're on an ARB or an ACE inhibitor? Typically ARBs end in TAN. So you might see this as losartan or irbesartan or candesartan. These are all TANs. They are angiotensin receptor blockers. We're going to talk more about what they do. So if it's true that they could increase ACE2 levels, it seems like it would be common sense that if you have more ACE2 receptors on the surface of your cell, now you've got more entry points for the virus to infect your cell. ACE inhibitors, they typically end in pril, so captopril and nalopril, and the list goes on. Those can also increase potentially your ACE2 receptors. And so what do we do with patients who are on ARBs and ACE inhibitors? Well, it seems as though people have a higher mortality who have a history of hypertension. And so this has led to a number of articles and a lot of social media to talk about, well, should we get off of our medications that we're taking for high blood pressure? So here is an article that was sent to The Lancet, was published on March 11th, 2020. And the question is, are patients with hypertension and diabetes mellitus at risk for COVID-19 infection? To understand this, you first start off with a hormone called angiotensinogen. And that is converted into angiotensin 1, which we'll abbreviate AT1. And that is done through an enzyme called renin that is produced by the kidney. Angiotensin 1 is then converted into angiotensin 2, and that is done in the lung by an enzyme called ACE. Now, ACE is in the lung. It does convert angiotensin 1 to angiotensin 2, and we can inhibit ACE by giving someone an ACE inhibitor. And these are the medication that end in prils. So captopril and lisinopril, etc., etc. So angiotensin II is a powerful vasoconstrictor. It also stimulates the adrenal gland to make aldosterone, which has the action of lowering potassium and increasing sodium concentration, and therefore increasing blood pressure. Angiotensin II is a major dividing point because there's two types of states that one can have in the body. So we'll call this the low state, and we'll call this the high state. On the cell membrane is a component of proteins that are sitting out on top of the cell membrane, and one of those is ACE2. And when there is not a lot of angiotensin II around, it is proposed angiotensin receptor 1, or ATR1, sits in the catalytic site of ACE2. Now, as it turns out, angiotensin II will be converted by ACE2 into angiotensin 1,7. And it's very important for you to understand angiotensin 1,7 because angiotensin 1,7 causes vasodilation and decreases inflammation. That's a good thing. It's also possible that you could put and have an angiotensin receptor blocker that would block this, and that is an ARB. So we've talked about angiotensin receptor blockers, and we've talked about ACE inhibitors. If you have high angiotensin II, this is the situation that you get. You still have ACE2, but the high levels of angiotensin II cause the angiotensin receptor to come off of ACE2. And when that happens, when angiotensin II interacts with angiotensin receptor 1, the result of that is vasoconstriction, increased blood pressure, increased vascular permeability, pulmonary edema, and presumably ARDS. Furthermore, when there's high angiotensin II, the hypothesis is that this opening in ACE2 allows for the coronavirus with its S protein to bind to ACE2. This binding here also requires something called a serine protease, known as TMPRSS2. Now that can be inhibited with something called camostat mesylate, and that is undergoing trials right now. Interestingly, when you have high levels of AT2, this entire complex can get degraded into lysosomes. So let's review quickly. We've got angiotensinogen being converted to angiotensin 1 by renin. Angiotensin 1 is converted to angiotensin 2 by an ACE enzyme. ACE inhibitors can prevent that from happening. If you have too much of angiotensin 2, then what can happen is this angiotensin receptor blocker dissociates with ACE2, and it gets activated to cause vasoconstriction, increased blood pressure, permeability, pulmonary edema, and ARDS. That's exactly what we don't like to see in these situations in viral pneumonia. However, if there are low levels of angiotensin 2, then what we see is that it gets metabolized by ACE2, and that gets converted into a vasodilator called angiotensin 1,7. Also, it looks as though ARBs, or angiotensin receptor blockers, can somehow keep this complex together and keep that catalytic site blocked by the resident ATR, angiotensin receptor. And that can happen with angiotensin receptor blockers. If it's high, however, this dissociation occurs, allowing the virus to potentially bind, according to the hypothesis, and that causes degradation. And you would predict that if angiotensin 2 levels were on the high side, you would expect there would be aldosterone and low potassium and high blood pressure. And that's exactly what they saw in very, very sick COVID-19 patients, is that they were hypokalemic, which means low potassium. And the most critical of these had higher blood pressure before they crashed.
Chinese National Center for Biotechnology Development Deputy Head Sun Ying-rong said that chloroquine, an anti-malarial medication, was selected after several screening rounds of thousands of existing drugs. According to Sun, patients treated with chloroquine demonstrated a better drop in fever, improvement of lung CT images, and required a shorter time to recover compared to parallel groups. The percentage of patients with the negative viral nucleic acid tests was also higher with the anti-malarial drug chloroquine, has so far showed no obvious serious adverse reactions in more than 100 participants in the trials. So, getting back to our idea here of what's going on in molecular, we've got zinc here that needs to shut down RNA-dependent RNA polymerase. And what we're saying here is that chloroquine is going to somehow open up this ion gate. Remember, zinc +2 ion, it cannot get into a cell. It will not diffuse. It needs to be transported somehow. And I think this is pretty exciting. So now this is a drug, an anti-malarial drug, that is acting as a gatekeeper to allow this in. So if we use our brains, there's got to be something that is not man-made that will also do this. But the proof is in the pudding. We need some randomized controlled trials. You know, we need to hit more areas on the corona. And one thing I want to start looking at is this ACE2 receptor. This is where this is binding. The S protein from the virus is exactly like ours, and it's lining up. And it looks so good that our cells like, here, take our ribosomes. We'll
get it going for you.
Are you ready? Get up, get up. 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 Well, are you ready now? From the revolution for too long, your power has been taken away. It's been taken away. Does your heart feel heavy now? Savor the solution. Take those mental shackles off and throw them away. You gotta get them out of your mind. Don't you let division leave you blind. Moving steady now. It's a revelation. For so long your focus has been taken away. Now you're breaking away. They may think they know you, but it's an education. No, they can't control you. Once you've broken away, they're done patrolling your mind.